Today we're going to talk about pH. The pH scale came about because it's really difficult to use the hydrogen ion concentration in everyday life because it's such a small number. So instead, we've used the pH scale that makes it way easier to measure the acidity of a solution. I think you recall from, I don't know, grade school that pH decreases as the hydrogen ion concentration increases. To calculate pH, you take the negative log of the hydrogen ion concentration. I don't know if you need this. But here's how you work your calculator. The negative log of the hydrogen ion concentration, I'm going to say it's 1.35 times 10 to the negative 8th. And that would give you a pH of 7.86. Does a solution that has a pH of 11.86 have more hydrogen ions or less hydrogen ions than this solution? Less. Remember, as the pH decreases, the hydrogen ion concentration increases. All right, really quickly, I hate to see you lose points on sig figs, so let's go over them really quickly. Okay, so only the numbers to the right of the decimal are significant in a pH. That's because of the logarithmic quality. So if I look at this, 0.00 are the only significant figures. If I take a hydrogen ion concentration that's 1.0 times 10 to the negative 7, only the numbers to the left of the x are significant. So there are two significant figures here. My pH should be with two significant figures as well. Okay? All right. Now, doing this negative log business where we use the small p can be used for other things too. You can take the equilibrium constant value, I don't know, let's say 5.6 times 10 to the negative 8th, and make it into a pKa as well. All you have to do is take the negative log of the Ka, and that will give you a pKa. Why would you want to use that? Because once again, it's a lot easier to work with than this small number. So, you can also find the pOH, which is the negative log of the hydroxide ion concentration. Therefore, Kw, which is a constant, is equal to the hydrogen ion concentration times the hydroxide ion concentration. The log of Kw is equal to the log of the hydrogen ion concentration plus the log of the hydroxide ion concentration. Therefore, pKa is equal to pH plus pOH. Kw is always 1.0 times 10 to the negative 14. pKw is equal to 14. If I take the negative log of this, it is 14. Therefore, pH plus pOH must always add up to 14.
What is the P?
It's the negative log of. That's a reminder to you, it's the negative log. Okay. Here we go. Calculate the pH and the pOH for each of the following. Okay.
No, I mean, what does it represent?
The negative log of.
Okay.
Okay, so if we have a concentration of OH that is 1 times 10 to the negative 3rd, the first thing we can find is the pOH by taking the negative log of 1.0 times 10 to the negative 3rd. That is equal to 3.00, 2 sig figs here, 2 sig figs here. I know that pH plus pOH is always equal to 14, so the pH is going to be 14 minus 3.00, which is 11. Be careful that you are answering the question that they give you. Likewise, if you have a hydrogen ion concentration that is 1 molar, that's a lot. The pH is equal to the negative log of 1.0 molar. That is equal to 0. Can you have a pH less than 0? Yep.
Yeah.
Yep. The H2SO4 that we work with in the lab has a molarity of 18.
Oh my God.
Yowza. Okay. So the pOH for this would be 14.
Wait, so what would that be on the, oh wait, I guess we could just calculate.
Yeah, we could. A pH of a sample of human blood was measured to be 7.41 at 25 degrees C. Calculate the pOH, H plus, and H minus concentration for the sample. So we know that pH is equal to 7.41. The way you get from pH to hydrogen ion concentration is this way. The hydrogen ion concentration is equal to the negative 10 raised to the negative pH. 10 raised to the negative pH. So 10 raised to the negative 0.714 is equal to, try this in your calculator just to make sure you can do it too.
3.89.
So the pOH of this solution is equal to 14 minus 7.41, which is 6.59. So likewise, the hydroxide ion concentration is equal to 10 raised to the negative pOH. So that would be 10 raised to the negative 6.59. And that would be whatever that is. Anybody know? Okay. Moving on. All right, ladies and gentlemen. What do you know about how strong acids dissociate?
Completely.
They do ionize completely. If I asked you for a list of all the strong acids right this moment in time, you would tell me they are.
HCl, HSO4, or H2SO4.
HClO.
NO,
HBr.
HNO3.
no sober clown, class clowns and
HI.
No sober class
HBr.
And what's the mnemonic?
no sober class
Isn't it
clowns.
HBO1?
No sober
Class.
clowns in
Idaho.
Hawaii or Idaho. Okay, how many of those? 2, 4, 6, we're good. Okay. Anything else is a weak acid, is that correct?
Yeah.
Yep, we know that. We know that strong acids dissociate completely. This is a, so if you have 1 molar HNO3, it dissociates completely into this. 0.1 molar HNO3 will yield 0.1 molar hydrogen ion concentration, 0.1 molar nitrate ion concentration. So the pH is equal to the negative log of the hydrogen ion concentration, which is 0.1, which means that the pH is 1. Likewise, if the hydrochloric acid will dissociate into this, so this little bitty amount will give you a hydrogen ion concentration of this, which is equal to the negative log. So the pH is equal to 10. Everybody good there? Same thing happens for a strong base. Strong bases are
OH, they have an OH in them.
that is true, they have an OH. I'm looking for the other bit.
It's the group 1 and some group 2, more massive group 2.
Group 1, and then some group 2.
Which one in group 2 are there?
You know what? It depends on some people call it calcium and strontium, but let's just go with group 1. This is the one that AP uses. Sometimes I contradict myself, but we should go with what they do.
Alright.
Okay, NaOH dissociates like this. So if you have 0.05 molar NaOH, you have 0.05 molar Na ions, and you have 0.05 molar hydroxide ions, correct? From that, you calculate the POH. POH is equal to the negative log of 0.05, which is 1, 2, oh, thank you. 1.7? Oh, it is 1.3. 1.3. The pH is equal to 14 minus 1.3, which is equal to 12.7. Do not turn yourself inside out messing around with a bunch of calculations if somebody asks you the pH, and that someone will be me, asks you the pH of a strong acid and a strong base and you're doing rice tables and driving yourself crazy. All I wanted you to do is remember it dissociates completely. Now, what doesn't dissociate completely?
Everything else.
Yep. And you know what? There's a lot of everything else out there. Weak acids and weak bases, you just moaned. Weak acids and weak bases do not dissociate completely, so they form an equilibrium system, and with hydrogen ion concentration and hydroxide ion concentrations, and they look a lot like equilibrium problems, and they require a I don't think that you are going to get away without doing a rice table. I saw people in 5th period thinking, I don't need one. That's not any of us in this class. We all need one. We're practicing doing all the work, so when we have to do it real quick, it's not that big a deal. Here is the longest problem on the planet. I will read it now. The hypochlorite ion, OCl, -1, is a strong oxidizing agent often found in household bleaches and disinfectants. It's also the active ingredient that forms when swimming pool water is treated with chlorine. In addition to its oxidizing abilities, the hypochlorite ion has a relatively high affinity for protons. It is a stronger base than Cl-, for instance, that forms the weakly acidic hypochlorous acid. Calculate the pH of a 0.1 molar aqueous solution of hypochlorous acid. Okay, if all of this made you a little nauseous and you didn't really know what to do, pay attention to the last sentence. It tells you what they want to know. Calculate the pH of a 0.1 molar aqueous solution of hypochlorous acid. Where is hypochlorous acid in any of this? HOCl. They've told you it's a weak acid, so there better be a double-headed arrow here. When it dissociates into solution, it forms, in solution it forms H plus and OCl minus, correct? And can you write a Ka for that? That's the value. This is the equilibrium expression. And they did give us that Ka is equal to 3.5 times 10 to the -8. All right, given that information, you can do a rice table and everything will be fine. HOCl, hydrogen ion, and the hypochlorous ion. That is our reaction. Our initial concentration of the acid is 0.10 molar, 100 molar. We have no hydrogen ions and no hypochlorous ions. The nice part about these problems is the change in equilibrium is always this way, because these always dissociate one proton at a time. So this change in equilibrium will always look like this. Always look like this.
Every single time.
So that will never be
Every
like
single time.
minus 2x.
Nope.
No, you have them right.
So, yep, 0.100 minus x, x, and x are our equilibrium expressions. Putting this into our Ka expression, we will write 3.5 times 10 to the negative 8 is equal to x squared over 0.1 minus x. Here's the other fabulous part about this. This is always disregarded. Always. Because the Ka values are always so small. Okay. So 3.5 times 10 to the negative 8 is equal to x squared over 0.1. X is equal to,
3.5 times 10 to the negative 9?
nope,
No, wait, never mind.
I got 5.9
Square root of that.
times 10 to the negative 5th. Anybody else?
Yep.
Okay, that is x, which is the hydrogen ion concentration. It also happens to be the hypochlorite ion equation, but we don't care. Then, to find the pH, we take the negative log of 5.9 times 10 to the negative 5th, and that is equal to 4.23.
We don't have to find the.
Nope, they didn't ask for it. All they asked was the pH.
So it's not unit.
For pH?
It's just number.
Okay,
It's too new for them.
now, what?
I just really like to make it numbers this unit.
Yeah, it's kind of
Go
nice.
back and still right, so do it.
So I have a question.
Okay.
The past equilibrium, you said that it was past times 10 to the negative 5th, that we just disregard the bottom.
Okay, we are, in all acid bases, you disregard all acid bases.
But you're still,
This is smaller.
but you're still using.
Isn't it negative log?
Oh, no, the only thing that you can disregard is this bit right here.
Okay.
Isn't it negative log?
Yeah, that's the only thing you can disregard. If somebody asked you how much was left at equilibrium, you would still do this math. All they wanted was the pH, so all we cared about was the hydrogen ion concentration. Okay. Now, let's say someone does not like you very much and determines that you are going to have to figure out the pH of a number of weak acids mixed together. Could be me. Could be me. I had to do it, so you have to too. Here's the good thing. Only the acid with the largest Ka value, otherwise known as the strongest acid, will contribute appreciable hydrogen ion concentration to the solution. Base the pH on the strongest acid and ignore any other acids. Okay, not a problem. Calculate the pH of a solution that contains 1 molar HCN, and here is its Ka, and 5 molar NO2 nitrous acid, and here's its Ka. And also calculate the concentration of the Cn minus ion in the solution at equilibrium. Okay, this is a short problem, which means sometimes they're kind of tricky. But you can do this. Which one's the strong acid? Right, so this is the strong acid. Why? Because 4.0 times 10 to the negative 4th is a bigger number than 6.2 times 10 to the negative 10. So, we're disregarding what this does for the moment, and all we are talking about is HNO2 dissociating into a hydrogen ion and the nitrite ion. The Ka for this is 4.0 times 10 to the negative fourth, and that's equal to the hydrogen ion concentration times the nitrite ion concentration over the concentration of the nitrous acid. Everybody with me now? Except for someone who may be sawing logs.
So maybe what?
Okay, the initial concentration of the nitrous acid is 5 molar. There's no hydrogen ions and there's no nitrate ions. The change to get us to equilibrium is always the same. So at equilibrium, good? So 4.00 times 10 to the negative fourth is equal to x squared over 5. X is equal to
.0447.
4.47 times 10.
0.0447.
Mhm.
That is equal to the hydrogen ion concentration. The pH is equal to the negative log of that, which is equal to
1.35.
1.35. So we have taken care of this part of the problem. Now they want to know the concentration of the cyanide ion in the solution at equilibrium. Well, the Ka for that particular problem would be equal to 6.2 times 10 to the negative 10 is equal to H plus Cn minus over HCN. Yes? Do you know this value?
Yes.
Yes.
It is. It's 1. Any other values you know?
Wait, how do we know that?
Why is the Ka equal 6.2?
Right.
We know the H plus.
We do know the H plus. How do we know the H plus?
We just
It's right here.
there.
But it was the H plus that belonged to that.
But
So,
it belongs to
H
everything.
plus is H plus, isn't it? So let's use that value. That H plus was 0.0477 times the Cn that we don't know. So we do know this. So the cyanide ion concentration is equal to, I got 1.39 times 10 to the negative 8. All right, that was pretty trigalicious.
So H plus is H plus.
H plus is H plus, it doesn't matter. Okay, let's skip over calculating percent association for today. Do not cross it off. We'll be doing it tomorrow. Something to look forward to. Let's quit using our pen caps as musical devices and do this. Are we doing this?
No. Let's call it a day.
No, I don't want to do enough. Oh, this is a percent association. We got 3 more things to do, so you just hold on. Calculate the pH for a 15 molar solution of NH3. Kb is equal to 1.8 times 10 to the negative 5th. What's the first thing you should do? First thing, anyone?
Write the balanced equation.
Write the balanced equation. This is step 1 for everything. Okay, NH3 and water All right, now what's going to happen? Which one's going to be the base and which one's going to be the acid? This is a stronger base than this is. So NH4, the base, received the proton, and the water donated it. So far, so good.
That looks familiar.
That does look familiar. So KB is equal to
So in that
NH4.
case, OH negative would be the conjugate A negative acid?
No, this was the acids in this conjugate base. Over NH3, why are we leaving the water out? Because, yeah, it can't fool us. It's pure liquid. So, in our rice table, we will have NH3, NH4 plus, and OH minus. Initial concentrations are 15 molar, 0 and 0. The change towards equilibrium is minus X plus X plus X. At equilibrium, 15 molar minus X, X, and X. 1.8 times 10 to the negative fifth is equal to X squared over 15. X is equal to
Is it always going to be Ka?
No. It's Kb. This is Kb.
Huh?
It's Kb if it's a base, it's Ka if it's an
Yeah, no,
acid.
but it's just.
0.0164 is what I got. That is equal to the hydroxide ion concentration. So the POH is equal to the negative log of that. The POH is equal to something teeny, 1.79.
How do you know that the Kb is 1.8 times 10 to the negative fifth?
It's given right there.
Oh. What?
So the pH is
Oh.
equal to 14 minus 1.79, which is equal to that. About time for you to do one on your own. Yay, you can do it.
Oh, is that
I will be giving you the methylamine is CH3NH2. Ready, set, go. CH3 methylamine?
Yeah. Did anyone watch that show?
Well, I did.
Sam, you watch that?
I don't watch that show.
I did
It
see
was
that
okay
you
for the
spell
first
America.
season, then it got kind of
Oh, yeah.
silly.
Yeah, this is basically the whole show. They're trying to find ways to get nothing.
Okay, I don't remember that. Who did I just discover was back?
Wait, is that meth?
Brian,
That's right. And,
Was it Brian?
listen, I got
is there anybody at, oh,
We're
so-
not food service.
Just put it up there.
Okay.
I swear, you just don't listen.
What did you defend for the
Not her.
Either me. But it's playing the part.
It's always fun. What's the complete
That's where the water comes in very handy.
I got HCH2.
There you go. You could- turn it
No, the water kills.
Okay. Yeah, this is a charge.
No.
You know what? Everything is wrong if you put the charge
Yeah.
back.
You what?
If you don't put
I'm
the
gonna put a
charge,
charge after.
everything is wrong.
No, not in your
Methylene is
equation.
base,
There's
yes.
big charge on the product. So.
What do you mean?
You get HCH3 and H2.
Wait,
This C, that CH3 and H2 is already on there. You're not checking. Just HCH3 and
Miss Adams.
Just as long as you don't go in front of him.
Then I go after him.
No.
What?
Everybody, good
Well, I was gonna wait till I finish this problem to ask.
I got it. Just don't have to do that.
I just label them A, B, C, and D for the rest table.
No.
Are you serious right now? I can't believe you even just asked
I
that.
don't want to write them all out.
Yeah, well, too bad.
I just told you why you have to do that. Oh, wait a minute.
Did you?
Yeah.
It's not just dragon.
I noticed you could.
I'm
spell
I'm
it.
starting to notice a little gender bias here.
Hey, hey,
Hey.
Let's not be sexist.
Not just
It's
doing
still
some
all upon us all.
observation, making a hypothesis.
Rude one.
You're not a psychologist, though. That's not what you're supposed to be making hypotheses about. Hypothesize? Whatever it's called. Who really cares?
Dude, we have to stick together. Come on. Yeah, guys. Hey, oh, like a plumber. Yeah, got the answer in the form.
PH situations are due on Friday. PH situations are due on Friday. Friday, not now. I got one more problem to go. And it's a big one. Okay, ladies and gentlemen, there is the problem. Moving on to the last one. For you, I believe it is number 5. No, I'm moving on. You guys are just gonna have to,